Thanks a lot for sticking around. So my name is Ben Stickler. I recently moved to the University of Ulm, where I want to directly start by acknowledging funding from the Carl Zeiss Q Photon Center. If you want to know more about this infrastructure, we have a booth over there, and you can get further information about how it is managed. It's a Carl Zeiss Center enabling collaborations between Stuttgart, Ulm, and Jena. And the main theme about this center is exploiting technologically quantum sensing and quantum applications using photons. Now, the research that I will be talking about, or the quantum sensing aspects I will be talking about, mainly grew out of research that I performed at the University of Duisburg-Essen and in collaboration with leading experimentalists at the University of Vienna. And I should mention that I'm a theorist, and what I will be talking about is how one can do quantum sensing, so quantum-enhanced sensing of acceleration forces and torques using optically levitated nanoscale dielectrics. So I won't be talking about two-level systems or qubits. I won't be talking about quantum computing. I will really talk about the mechanical motion of extended dielectric objects which strongly interact with light fields, and how observing this mechanical motion can allow us to sense external forces and torques with a precision that exceeds that is achievable with classical systems. I will start by giving you a short introduction about how quantum sensing can achieve an advantage when it comes to the mechanical degrees of freedom. And what lies at the heart of such quantum sensing applications is the quantum superposition principle. The quantum superposition principle is a basic property of quantum theory as we know it. And it expresses the fact that an arbitrary system can be brought in a quantum superposition of being in two different locations at the same time. Any mechanical degree of freedom can exist at two locations at the same time. And that quantum superposition principle has been tested over the decades many, many times, and it is a well-confirmed experimental fact of nature. And just to give you a short history, so the first demonstrations of quantum superpositions were experiments of a double-slit type, where you can see interference of single electrons and protons, which pass through two slits simultaneously. Now, it's not very impressive to see this with electrons and protons because they are not very massive, but people moved on, and today atom interferometers, which do the very same thing with massive atoms, are amongst the most precise acceleration sensors that we know about. So an atom interferometer, easily speaking, consists of 3 laser pulses, where the first where a single atom or a cloud of atoms that is not interacting is brought into a superposition by the first laser pulse, so a superposition of being not kicked, so just continuing on a classical trajectory and being kicked. So at this state here, the atoms are in a superposition of being along this branch and that branch. Then with the second pulse, you close the interferometer, and with the final branch, you read out the superposition. And now it turns out that if these two branches, for whatever reason, experience slightly different forces, you can measure the difference in the force extremely precisely through the phase that is accumulated in this atom interferometer. And this scheme allows, for instance, acceleration sensing on the order of nanometer per second squared. Just to give you an example, the current record for the most precise force sensing application with an atom interferometer comes from the lab of Holger Müller at Berkeley. And what they do is they create a superposition of an atomic cloud of being at 2 different locations, separated by roughly 10 micrometers. And they hold this superposition for 70 seconds. So 70 seconds is really a macroscopic timescale. There's a lot of things that you can do. And since the accumulated phase difference increases with the time that you wait quadratically, you can really learn a lot and measure extremely precisely, for instance, the gravitational interaction of the atomic cloud with a tungsten cylinder at a distance of several centimeters. So just for comparison, in 70 seconds, the world record holder of the Rubik's Cube can solve this thing 17 times. But what I want to focus on today in this talk is not about sensing with atom interferometers, but using larger and more massive objects. And just to give you a short history of molecular interference and nanoparticle interference, since the quantum superposition principle is universally valid, there shouldn't be or as far as we know, there is no boundary to our ability to create these superpositions. And the current records for seeing double-slit interference with massive particles comes from the lab of Markus Arndt in Vienna, one of my collaborators, where they probe double-slit interference with molecules that contain thousands of atoms. So just to show you one of those movies, so these individual dots are individual molecules which arrive at interference grating, and if you wait long enough, you can see the interference stripes building up. It's always only a single molecule in the interferometer, so it's not a molecule interacting with the other molecules, like in water waves. It's really the quantum nature of the motion of each individual atom. So there's a close-in. You can see, if you average over 1 million molecules, you can really see the interference fringes to build up. And now the important thing to note is that the precise shape of these interference fringes very sensitively depends on any external forces and torques that might be applied to the interferometer. So this can be used for molecular metrology to measure the molecular properties with unprecedented accuracy, but it can also be used for measuring external forces acting on the interferometer. Now here, a short history of molecular interferometry. It started in 1999 with Anton Zeilinger's experiment, where Markus Arndt was the first author, with buckyballs, small footballs containing 60 carbon atoms, and they quickly moved on to more complex and more heavy things. So this was the record like 5 years ago, and the current record for the most massive superposition is from 2019. It's a molecule containing roughly 20,000 atomic mass units. So 20,000 atomic mass units, that's 20,000 hydrogen atoms, so about 2,000 carbon atoms. Right, but that's not the boundary. I mean, that's not where we stop. So what we want to do is we want to create superpositions of even heavier particles. And there has been a recent breakthrough in the field of levitated nanomechanics or levitated optomechanics by the lab of Markus Aspelmeier, also in Vienna, also one of my collaborators, where they succeeded in cooling the motion of a dielectric sphere. So the dielectric sphere is here in the center of an optical tweezer. It contains roughly 1 billion atoms, so 10 to the 10 hydrogen masses, and it's trapped in an optical tweezer, and via its interaction with a cavity mode, it can be cooled into the quantum ground state. And so you localize the position of the sphere on a length scale that's associated to the 0-point motion in this harmonic potential, which is below femtometers. And by localizing it so precisely and being able to read out slight motion of this sphere, you can also realize extremely precise force sensors, which are only limited by the quantum uncertainty of the state. And that's what I will mainly be talking about in the next 15 minutes. So the main questions that we are interested in this research is whether there's a fundamental and mass or a complexity limit to our ability to create quantum states of massive systems. So that's the academic question. But then the technological question is, given that we can prepare such states, how can we use them for sensing beyond the capabilities of existing technology? And that's what I will focus on today. Now, the basic ingredient of this field of levitated nanomechanics is an optical tweezer and a dielectric particle that's trapped in the focus of the tweezer. So an optical tweezer excites a polarization field inside of the particle, which leads to a dipole attraction of the particle to the focus of the tweezer. So it's a high field seeker, like the Rydberg atoms that Tillman was mentioning before. And since the laser field oscillates with the optical frequency, this dipole field is also oscillating and radiating away. And detecting the scattered light, so this radiation, allows us to measure the position of the particle extremely precisely and to apply forces to the system based on the change of the scattered light. And this can be used to implement feedback loops and to cool the particle motion into the ground state and to read it out very precisely. There are many different levitation platforms, ranging from atomic systems all the way up to trains. Now, our levitated particles are on the range of sub-millimeter to hundreds of nanometers length scale. And so why is it interesting to levitate things in that length scale? Well, people identified roughly 4 different main motivations for this. So I will be mostly focusing on the quantum science and the sensing part, but I want to mention that people are also very interested in the fact that you have an extremely isolated solid state system, which contains 1 billion of atoms. So it's a solid state system, but it's extremely well isolated, and you can do a lot of things to it. You can apply strong forces, stresses, and you can learn a lot about phase transitions and similar things. And then there's a large community who does classical simulation or classical analog computing by performing simulations of complicated stochastic systems, and they are also interested in this levitation platform. But I will be mainly focusing on the other two aspects. People are levitating all sorts of funny things. It's not always spheres like we imagine it. It's mostly these funny-shaped potatoes or dielectric rods, elongated things, or even dumbbells. And sometimes it looks like a sphere, but it's not really a sphere because it is slightly deformed. And why is it important that these things are not perfect spheres? That's because they can rotate. They will rotate unavoidably. They will always rotate. So we want to control a levitated particle. What we actually have to control is its 3 center of mass degrees of freedom and its 3 rotational degrees of freedom. So that makes 6 degrees of freedom that we have to keep under control, and that we can also use for sensing applications. There is 3 different platforms that people are currently using for levitating these kind of things. I already mentioned the optical tweezer trap. Then, of course, you can also use electric and magnetic traps. Electric traps work like for ion traps, for atomic ions. You just charge your particle and put it in a quadrupole ion trap, in a pole trap. You have to be aware that since the particle is not perfectly spherical and since you will have electric dipole and quadrupole moments, also the rotational motion will be strongly affected by the trapping fields. But in principle, the basic working principle is the same as for atomic ions. Magnetic traps is something which is upcoming. The disadvantage of the magnetic traps is that they are very low frequency, which makes it tough to reach the quantum regime. But at the same time, they are extremely high. They have extremely low noise levels, which makes it advantageous for long-time measurements of external forces and torques. So they usually use diamagnetic levitation or permanent magnets above superconductors and flux pinning. So over the last 10 years, people in the community of levitated nanoparticles have developed all sorts of different tools to control the motion of those particles precisely. So I'm just bringing this picture from this nice review of Carlos González Ballesteros, which was published in Science last year. So we don't have to go through all of those things, but let me just mention these particles have internal and rotational degrees of freedom. You can explore conservative versus dissipative dynamics. You have the freedom of shaping the potential, which contrasts these systems to clamped optomechanical oscillators, which are always oscillators. So here you can also have double wall potentials, inverted oscillator potentials. And you can measure their position very precisely and apply either active feedback via measuring the motion and applying forces conditioned on the measurement, or passive feedback via placing cavity mirrors around, which act as a passive feedback loop. People have thought about hybrid potentials where you combine magnetic, electric, and optical techniques, and people have also thought about entangling the nanoparticle motion to external degrees of freedom, such as embedded NV centers or external superconducting qubits. Most importantly, these active and passive feedback cooling schemes, both of them, have demonstrated the capability of cooling the motion of a 100 nanometer sized object to the quantum ground state in an optical tweezer trap. So that was a big breakthrough in 2020 when Uro Stelic succeeded in cavity cooling a sphere to the ground state, and not so long after that, people also succeeded in 2 different teams. So Uro Stelic is from the team of Markus Aspelmeier in Vienna, and then 2 teams, again the group of Markus Aspelmeier and a group of Lukas Nowotny in Zurich, succeeded in feedback cooling the motion of a similar sized sphere also to the quantum ground state. What makes nanoparticles special, I also already briefly mentioned it, is the fact that they can rotate. What makes rotations interesting? Rotations are inherently nonlinear. And I always like to show this movie, that's why Cyprian is already laughing. This movie is from the ISS. It shows the rotational motion, a free rotational motion of an asymmetric rotor. An asymmetric rotor is a particle with 3 distinct moments of inertia. And you can see that this motion is highly nonlinear. It flips between pointing in 2 opposite directions periodically, and that's the integral free dynamics of this particle. It's highly nonlinear because Euler's equation of motion are nonlinear. And that's a challenge because that means it's very tough to control the rotational motion of a nanometer-sized particle only with optical, electric, and magnetic fields at the quantum limit. But also, it's a big advantage because these dynamics very sensitively depend on the presence of external torques. So measuring these dynamics is also a tool for sensing the environment very precisely. Now, in the field of levitated optomechanics, we have developed the techniques to control the rotations of aspherical ellipsoids quite recently. That was a paper from my group, where we devised a technique to control all 3 rotational degrees of freedom by using elliptically polarized tweezers and a cavity placed around it to cool all 6 degrees of freedom of the particle simultaneously. So that was a theory proposal, and it was recently implemented experimentally in the group of Peter Parker at UCL in London, reaching millikelvin temperatures in all 6 degrees of freedom of a levitating particle. That's not yet the ground state. So the ground state had only been achieved in the center of mass motion, but it's 2 orders of magnitude away from the ground state, and the experimental, so it's clear under what experimental conditions this will be achieved, and that's something that we can expect in the near future. What do you gain from cooling the particles to the ground state? Well, you gain the possibility to sense external forces or accelerations very precisely, because each force or acceleration that acts on a particle will displace it from its minimum in the harmonic trap, and that can be measured very precisely. Roughly speaking, there's 3 different techniques of how you can use that. You can use it as an DC sensor, where an external force, a constant force, acts on a particle, a homogeneous force. And you do that by cooling the particle, switching off the trap for a very short time, a few nanoseconds, switching it back off, and measuring the amplitude of the motion. So that allows you to sense a DC force. Then you can also always measure short pulses of forces, which are on a time scale shorter than the oscillation period of the particle. And then you can use this thing as a resonant force sensor, where the force is resonant with the oscillation period of the particle. The currently realized force and torque sensitivities are on the order of septonewton per root hertz and on the order of 10 to the minus 13 newton meter per root hertz. But I should probably mention that this is of course a very competitive force and torque sensitivity, but that's still purely classical. So that's limited by the quantum uncertainty and shot noise of the particle, but it doesn't use quantum interference for boosting the sensitivity any further. So that's roughly the timeline. So we are here. Ground state cooling is a reality, has been achieved in several labs. Now up to 5 labs, I believe, have already achieved ground state cooling of levitated particles. So what's the next steps that we are going to do? Of course, people will start looking for quantum superpositions on the level of single-digit harmonic oscillations of the particle, but that's not very macroscopic, and that's not very sensitive to external forces. What people really want to do in the long run is they want to somehow create large delocalization, quantum superpositions of the particle over a length scale that's comparable to the size of the particle itself, because then the particle really starts to get very sensitive to external forces and torques. There's various ways of how this can be achieved, and I will be speaking about one of them in a second. And then another big goal is, of course, generating entanglement. And along this road, going in the direction that Tilman was mentioning in a previous talk, of having an array of particles which can be strongly interacting via optical fields, and using this interaction for realizing arrays of particles as force-sensing arrays. So I will be speaking about an example for that in a second. And then there's, of course, this fundamental quest for creating macroscopic quantum superpositions for probing the boundaries of what we know about the validity of the quantum superposition principle. But I won't be talking about that. So let's briefly talk about this part. How can we generate quantum superpositions that are large? So usually people think about generating a large superposition of something which is here and there, right? But these particles I already mentioned, they can rotate. So this gives us a little bit more freedom. So what actually people are also thinking about is creating a superposition of a particle pointing in 2 different orientations at the same time. That's equally macroscopic, because that means that most of the atoms in the particle are in a superposition state, which is delocalized over a length scale that's comparable to the size of the particle. And one scheme that would achieve this is uses what is known as orientational quantum revivals in the molecular physics community. It's a very simple observation. It's the only equation that I will show. It's the fact that if you have, so you can have an initially aligned particle. It points in a well-defined direction in space, and then you just release it. And you assume that there's no external forces, there's no whatever, no environment. Then the free dynamics of the rotor is described by the unitary time evolution operator, and that prominently includes the spectrum of the rotor. So J times J plus 1, J is the total angular momentum quantum number, and the spectrum of a rotor, maybe you know that from molecular physics, has this peculiar structure of being J times J plus 1, so the level spacing increases with J. Now, just mathematically, if j is an integer, j times j plus 1 is always an even number, which means that there is a time scale called the quantum revival time, which is completely determined by the moment of inertia and by h bar. So it's a purely quantum time scale on which this number here is always an integer multiple of pi. So it means, 2 pi, sorry. So it means that this entire time evolution operator is always the unity operator. Or in other words, the particle perfectly comes back to the initial orientation that it started out with, irrespective of what this initial state actually was. And that's a purely quantum phenomenon. There's no classical analog for that. And that's an artist illustration of how it would look like. You start out with a state, it has an uncertainty in the angular momentum. Then you switch off the trap. It starts rotating in all possible orientations. And at the revival time, it perfectly comes back. And that's a strong quantum signature. That's a quantum interference effect. It's fundamentally due to having a state in a superposition of angular momenta and the fundamental quantization of angular momentum. And it turns out that also this phenomenon very sensitively depends on the presence of external forces and torques. And a protocol to observe this with nano. So I should maybe also mention that this effect has been observed with molecules of a size up to a dozen atoms, roughly. But it hasn't been yet observed with nanoparticles, and the reason being that this time scale of the revival quickly becomes very large. So for this laser point, it would be longer than the age of the universe. For a 50 nanometer silicon nanoparticle, it's roughly on the order of milliseconds. And that's a protocol that would allow us observing this effect and using this interference effect for torque sensing. And it roughly contains 3 steps. So the first step is trapping the particle in a tweezer. So that's not cavity mirrors, that's just the lenses of the tweezer. Then cooling it via feedback cooling close to the ground state. It doesn't need to be the ground state. It's sufficient if it's millikelvin temperature. So actually it would be doable with the particles in London. Releasing it, waiting for the revival, measuring the precise timing of the revival, trapping the particle again, and restarting. Like in quantum computing, since this is a quantum interference effect, you have to repeat the experiment over many, many, many runs in order to really see the interference pattern to build up. But that's a doable experiment, and people at several locations are currently working towards realizing this interferometer experiment. Now, in the last 7 minutes, I will briefly talk about our recent research into going in this direction of exploiting many particle quantum states of levitated nanoparticles. That's research together with the group of Markus Aspermeier in Vienna. And it has been recently published. The setup is, the easiest setup is 2 particles levitated next to each other, each in an individual tweezer, having tweezer arrays like Tillman V in principle, distance being several micrometers. And now these particles start interacting because the light field induces an internal polarization field which radiates. And now the radiated field interferes constructively or destructively with the trapping field of the other particle, which leads to an effective interaction. Now, whether this interference is constructive or destructive depends on the precise location of the particle, so you get a strong coupling between the motion of the 2 particles. This is fundamentally an open system. So there's light also scattered in all possible directions, which does not contribute to the interaction. So there is no necessity that the dynamics are conservative. So what that means is the motion of the 2 particles is 2 independent oscillators which are linearly coupled, but there are 2 different types of coupling constants. One of them is the normal conservative coupling constant that we are used to. I call it K1, but there's also a non-conservative coupling constant which appears with opposite signs. And what that means is that one particle attracts the other, but the other repels the first one. So it's a weird type of interaction. It violates Newton's 3rd law, but that's not a fundamental problem because a lot of information is scattered away to infinity by the light field. These type of interactions are known as non-reciprocal interactions, and they are very important for several sensing technologies because what it means is I can have a force acting on this, so I can tune the 2 interactions such there's only a force from set 2 onto the first oscillator, but not the other way around. So I can use one of the 2 particles as a readout, and the other one is the particle which actually sends the interactions, and there is no measurement back action onto the particle, classically. Quantum mechanically, that's not perfectly correct, but that's on a different note. So this has been observed in the lab by Markus Aspelmeier. So that's measuring the conservative interaction. So that's the power spectrum, so the Fourier transform of the particle motion over a long time as a function of the two different frequencies. So eta is the fraction between the two trapping frequencies. And you can see nicely an avoided crossing because of the interaction of the particles. Now, if you go to perfectly non-reciprocal interactions, you get what is known as normal mode attraction. So you get a non-Hermitian effective type of dynamics where one of the two normal modes starts exploding exponentially. And that's why this agreement here, why the experimental data does not agree with the dashed line, which is not the theory prediction, but should just indicate the normal mode attraction. So quantum mechanically, I already hinted at it. One can also, so if these particles are cooled to the quantum regime, then the quantum nature of the light field starts mattering. And what this means is that there will be correlations in the shot noise between the two particles. And these correlations are actually interesting. So this can be mapped out as a function of the distance and the relative phase between the two tweezers. You get different regimes. You can get the regime of reciprocal interaction, of anti-reciprocal interactions, and you can get a regime where the particles are not coupled, but only effectively through noise correlations. So we probed this experimentally recently. I will show it in a sec. I just want to mention that having two particles in the vicinity of each other can also be used for differential force sensing. So in this paper here, we demonstrated, also together with the group of Markus Aspelmeier, that in principle having two spheres separated by 5 microns allows sensing of force gradients on the order of septonewton per micrometer per root hertz. Yes, 10 to the minus 21 over micrometer. Right. So here you can see a regime in the different in the reciprocal versus anti-reciprocal coupling constant, where time reversal symmetry is effectively broken, and you get this strong normal mode attraction. So this region here is here rotated. And that's the theory prediction. So inside this time reversal symmetry broken phase, you expect mechanical lasing, a mechanical lasing transition where the motion of the two particles gets excited into a highly populated coherent state, and they start moving on a classical limit cycle, which is very sensitive to, whose phase can be very sensitive to external forces. And that's the first experimental data has been put on the archive a few days ago, where we actually demonstrated that in the lab of Markus Aspelmeier in Vienna. All right. That's it. I wanted to present to you the platform of levitated nanomechanics as a very promising tool for sensing at the quantum limit and beyond the quantum limit. Levitated nanoparticles differ from other levitated systems in their very precise control and readout. I mentioned rotations as a novel degree of freedom that might be very useful for future applications, and which also makes the physics quite interesting. And I also briefly mentioned the ability to have highly tunable interactions. Thank you very much. We have 2 minutes for questions. What do you mean?
If you want to tune the ratio between the capital omega and k, the interaction between the nanoparticles and the frequency of their motion?
Yes. So the frequency. So the question was how you can tune the different parameters appearing in the equations of motion, in particular the trapping frequency versus the coupling strength. The trapping frequency is predominantly determined by the power of the individual tweezers. So by just increasing the laser power, you can make the trap more stiff, with the constraint that at some point the particles start absorbing photons and then melt. So you lose the particles. So there's a limit to that, but you can tune it over. You can tune it from having from kilohertz to megahertz roughly. The interaction is determined by the distance between the two particles, also by the tweezer power, but you can independently move it via the distance and via the relative phase between the two tweezers. Via the relative phase, you can also tune independently the strength of K1 versus K2. Yes.
Actually, it's a general question.
Yes.
You know that starting from light interferometer, electron interferometer, molecular interferometer, there should be some limit. Do you know?
Okay. So the question was, if you go to ever more massive systems and you want to see the quantum superpositions, if there's a fundamental limit. So as far as we know, there's no indication whatsoever that there is a fundamental limit. So the current state of knowledge is that the quantum superposition principle holds universally. So quantum physics is valid on all mass and complexity scales. That said, it hasn't been probed for systems more massive than these 20,000 atomic mass units due to the technological constraints. The limiting factors at the moment are mostly decoherence due to the environment, and also the fact that it's not so easy to make these particles fly through an interferometer in a stable and reproducible way. But people are working on this and pushing it ever further. So I know that Markus Arndt is currently pushing towards more massive systems. So he's soon going to beat this 20,000 atomic mass units record. And then on the nanoparticle scale, there's also a lot of progress towards seeing massive superpositions. Nanomechanical cantilevers have seen superpositions of objects that are much heavier, nanograms, but only on a very, very small length scale. Below femtometer. So there's different, there's not only mass, there's also time scale. So in fact, having a superposition over 70 seconds, like in the atom interferometers, also is competitive to these more massive superposition experiments when it comes to ruling out alternative theories to quantum physics. Yes. So there's different aspects, but as far as we know, it holds universally. Good. Then thanks again for the attention.